astronomical monsters, the devourers of suns, the end of time itself. Black holes have captivated and tormented physicists for decades.
Until very recently, we thought we had a handle on how black holes formed in the violent deaths of massive stars. But now it seems that might not always be the case. Observations from the James Webb Space Telescope are overturning everything we thought we knew about how the most massive, supermassive black holes form and how the early universe evolved. In search for answers, tonight we are journeying to the edge of the event horizon and back to the cosmic dawn. Welcome to the Sky at Night. For the last 4 years, JWST has been turning the world of astrophysics on its head. When astronomers pointed it at the sky, they were surprised to find the cosmos covered in dots, little red dots.
It was in mid-2022 that the James Webb Space Telescope, or JWST, started to see the little red dots, a new and completely unexpected type of object. And they're truly ancient, beginning to appear in the universe's infancy less than 1 billion years after the Big Bang. Most are compact, only a fraction the size of the Milky Way, yet bright, way too bright, outshining entire galaxies. Growing evidence suggests that at their heart lurk huge, hungry black holes, some with masses many millions of times that of our Sun.
But there's a mystery. How did these black holes form so early and get so big so fast?
We've learned so much from black holes. Studying them has led to breakthroughs in our knowledge of gravity, quantum mechanics, and even precision manufacturing. And now, with JWST's observations of little red dots, it seems that black holes are presenting us with a whole new set of mysteries. I'm here to meet an old friend who knows all about black holes to find out what more there is to learn. Hey Brian.
Hi.
How are you?
Very well, thank you.
Have a seat.
My favourite subject.
Yeah, well let's start with an easy question. What is a black hole?
It's not a simple question, but historically it's a fairly simple answer, which is that it's a star, a massive star that's run out of nuclear fuel and is collapsing under its own gravity. And if it's sufficiently massive, nothing can stop the collapse. And so it collapses, in a real sense, out of existence.
Einstein's theory of general relativity predicts something extraordinary. If an object is massive enough, its own gravity can cause it to collapse, bending space and time to an infinite point. This singularity lies at the dark heart of every black hole. Take me on a tour of your favourite black hole.
So let's say it's Sagittarius A star, which is our local supermassive black hole, right? Centre of the Milky Way galaxy. So as you approach it, you see this disk of material, and it would be a disk of material, which is, you think of it like Saturn's rings, a flat disk of material, glowing bright, orbiting around the black hole. But you wouldn't see it like that because of the distortion of the fabric of the universe. You see it, this famous sort of donut shape of a black hole, that we're all familiar with from films like Interstellar.
Yeah.
If we're watching our friend approach it, then we'd see our friend get closer and closer to the horizon of the black hole. And ultimately, we would never see them cross the horizon into the interior of the black hole. We'd see time stop.
So this horizon is the point at which not even light can escape from there.
Yeah, so the horizon it's for us from the outside, you could say, well, it's the region of space where everything is so distorted that the time stops from our perspective. But as far as Einstein's concerned, from the perspective of the person going in, you just fall in. And then you carry on and you start to approach this singularity. What happens to you then? You could get quite close, we think, to the singularity, but you get stretched in one direction, squashed in the other, and it's called spaghettification for a good reason, because you get turned into spaghetti. Even the atoms out of which you're made are ripped apart. And then ultimately our knowledge fails. Space ceases to have a meaning. Time ceases to have a meaning. People say, I don't understand that. And the correct response is, yeah, nobody does. That's why they're cool. Einstein, really, I think it's fair to say, till the day he died, 1955, didn't really think these things would exist because it's just absurd.
And yet, not only do they exist, but they're common. And they're at the heart of every galaxy we've seen as well.
Yeah, for reasons we don't fully understand.
So how massive are these things?
There's a bit of a disconnect, isn't there?
That's right.
They're
I
not
think that's
continuous.
interesting.
They're the smallish ones, which are the 10 to 100 solar masses. And then there are the big ones.
Black holes seem to fall into two groups. Those with up to about 100 times the mass of our own sun, and supermassive black holes, giants equal to hundreds of thousands, millions, or even billions of stars.
So the M87 black hole, which is the first one we imaged from the Event Horizon Telescope, happened to be 6 billion times the mass of the sun.
Some supermassive black holes are ravenous, unleashing vast amounts of energy as they feed on nearby matter. And now it seems that these may help us explain the little red dots that JWST is seeing.
Black holes, a bit like me, are super messy eaters. As their meal comes towards their mouth, the immense forces of gravity tear it apart. Even atoms get shredded. And what you're left with is a disk of super hot plasma, an accretion disk.
Dr. Emma Chapman researches the early universe. But can her studies shed some light on a possible link between the accretion disks of big black holes and the little red dots?
So Emma, can you tell me about your research?
I try and work out the answers to questions about the early universe that we haven't quite figured out, particularly to do with the first stars and the first black holes and the first galaxies.
The archaeology of the universe.
Exactly that, but with telescopes instead of trowels.
What is a little red dot?
Well, I can show you. Here's some we found earlier. And what's key here is that they are all small, they are all red, and they're all dot-like. We only see them within about the first 2 billion years, and they kind of peter out.
It's like a phase that the universe went to, sort of developed these little red dots, but then passed through and went out the other side.
Yeah, it's a teenage rebellion. It is a teenage rebellion because we did not ask for this when we turned JWST on. We were perfectly prepared to look back really far and see some first galaxies. Great. We were not expecting to see an entirely new class of astronomical object, which quite frankly has been distracting for the last 4 years. But they have also been a gift.
There have been many weird and wonderful explanations to account for the little red dots. Some thought that they might be explained by star clusters, which would need to be close to impossibly dense. Others theorized dark stars, huge suns powered not by fusion, but by the annihilation of exotic dark matter. But now, one idea seems to be gaining traction.
There's a lot about them that is kind of lending evidence to them being black holes. Possibly an active galactic nuclei. So a black hole with a big accretion disk around it. So we think what we're seeing is almost like an evolutionary stage of something that we know a bit more familiarly close to us.
Yes.
Some supermassive black holes produce active galactic nuclei, the most extreme and luminous objects in the known universe. They are caused by the rapid feeding of a few of these supermassive black holes, and they can outshine entire galaxies.
So can you tell me more about these active galactic nuclei?
It's a horrible name, isn't it? But the idea is it's a black hole which has an accretion disk around it, and this black hole is feeding on the gas and the dust, and this is swirling into the black hole. And as it does so, there's lots of friction, lots of heat, and normally that's what we see when we say we see a black hole.
Yes, because you can't see the black hole itself.
Yeah, it's usually the glow of this disk.
Yes.
So this actually goes some way to explaining a lot of the little red dot activity. JWST has done a fantastic job of actually zooming in to specific little red dots now.
Yes.
They're actually able to measure how quickly the gas is going around in the centre.
Yes.
And what they found is it's going around so fast that the only thing that can really cause that is a black hole.
Yes.
But they're still too massive to really explain with any of our models, or my model certainly, for how to build a galaxy. Which means we're looking at an early universe where possibly the first black holes were forming at the same time or before the first stars.
The traditional understanding of how the universe evolved starts with matter being generated in the Big Bang. The matter then slowly cooled until the first stars formed. Some of those stars grew so large that they eventually collapsed to form the first black holes. The trouble is, we find little red dots far too early in this cosmic history. Their supermassive black holes appear to weigh tens of millions of times the mass of our sun. To grow that big should take many billions of years.
Ooh. Yes. Okay, that takes a bit of thinking.
Yeah, it does. It's a bit of a pain when you've spent a decade creating models which really rely on this kind of strict narrative, if you will, of early universe, very Big Bang energy, calming down, gas cooling, forming stars. Stars die into black holes. And now we have to work out, okay, how do you grow a black hole that fast?
Yes.
This must mean either the stars formed much earlier than we thought, or there's a way of creating black holes without stars. Because the thing that people most miss about black holes when they're trying to understand them is that they're not just destroyers, they're creators as well.
Yes.
So when it comes to black holes, you really need them to explain the architecture of the universe. They are the architects of the growth of galaxies. They make sure that the gas is processed and mixed and gets to the right places. And without them, it's very difficult to build and maintain galaxies.
Yes.
So yeah, as much as they have this bad reputation, they are absolutely vital.
Whatever the little red dots are, studying them leads to some crazy ideas. So let me show you what JWST's been finding. So this is the first one. So this is a cool object. So this is Glimpse 17775. So this is a galaxy cluster, and then this is a lensed object from behind.
Yeah, so you can see the lensing there.
Exactly. So this thing's down in the corner, and it's a massive black hole, the center of its own cocoon of gas. And it's growing while surrounded by this hot gas. So it's 10 to the 6 already.
Yeah, it's as massive as some black holes at the hearts of galaxies today.
This is it's about the same mass as the Milky Way's black hole. So the suggestion is this is almost something a bit like a star, but at the center, instead of nuclear reactions, you've got a black hole that's still growing. And so to get it to grow this fast, so you've got a sort of zombie star that's already produced a black hole at the center, but it hasn't blown off the outer layers and it's still growing. If Glimpse 17775 is a black hole star, one theory is that it was a relic of the first generation of stars, which we think were massive. As some of these stars formed, their cores collapsed directly into black holes, without the enormous explosions that normally blast off surrounding material. Instead, a massive newborn black hole remained shrouded in a vast cocoon of gas. And Glimpse isn't the only puzzling little red dot found by JWST. And then there's another cluster. So this is a different cluster from JWST. We're going to look down here, and this is really cool. So there's the galaxy cluster. But if you look at these are three images of the same object.
Yeah.
So there's one object behind the cluster, and then it's lensed 3 different times. So it's like looking through a funhouse mirror or something. It's early universe again. We're in the first billion years. And this little red dot has a black hole and almost nothing else. So it's got some hydrogen and helium, but it's just the black hole. Late in 2025, JWST spotted a little red dot called QSO1, travelling through space some 13 billion years ago. Analysis led to a startling conclusion. The black hole at its centre was a behemoth, 50 million times the mass of our Sun, making up 2/3 of the host galaxy. Because of this size disparity, QSO1 seems to have formed before its galaxy. Astronomers need new ideas to explain objects like this. So what about this idea that this could have been a primordial black hole that then grew? Could we have formed black holes out of the Big Bang without a collapsing gas cloud?
In particle physics terms, the answer would be yes. There are many theories, but what they tend to have in common is that as you go up in energy, so at higher temperatures, you find that gravity can become strong, much stronger. So it's very, very weak today.
Yeah, we know this because we can jump even though the whole Earth is pulling us down.
But you're going back in time now towards the Big Bang, where gravity becomes very strong. Then you can make black holes.
Another theory is emerging as a frontrunner to explain at least some of the huge black holes found at the centre of the little red dots. Direct collapse from massive clouds of gas without the bother of first forming stars. Is it a direct collapse?
From a physics, a theoretical perspective, it doesn't matter. You put enough stuff in a region of space.
It's enough stuff in a small enough region of space. That's the recipe, right?
That's it. So it doesn't have to form from a star. Well, certainly theoretically it doesn't. Then, of course, which is the interest, right? You're asking questions about the distribution of matter in the early universe.
Right.
And whether there are regions that are dense enough to go straight to black holes.
Direct collapse black holes could be the origin of the monsters thought to lurk at the centre of the little red dots, because of something called the Eddington limit. This is the theoretical maximum speed black holes can grow. Pour material in more quickly than the Eddington limit, and intense radiation will push back, slowing things down.
According to the Eddington limit, there is simply not enough time for a black hole to be born and grow supermassive as early in the life of the universe as JWST is detecting them.
The work of Professor Zadeh Koshvar at the University of Edinburgh may go a long way towards overcoming this obstacle to explaining the little red dots.
So, Zadeh, tell me, what is a direct collapse black hole?
Oh, it's the most amazing object you can imagine. A direct collapse black hole is a black hole that formed from a huge gas cloud that was so heavy that it collapsed under its own gravity in the early universe and went directly into forming a black hole.
So, how is it then that direct collapse black holes can help us understand the fact there are black holes that are supermassive so early in the universe?
So these direct collapse black holes, they give us a head start because they form roughly something like 200, 500 million years after the Big Bang, but they already are born with a mass that is roughly 10,000 to 100,000 solar masses. Direct collapse black holes help us jumpstart by being already so much more massive than the other ways.
So have you actually seen these forming at all?
Seeing a black hole forming is very, very difficult. And we have not seen them forming, but we have indirect evidence for their existence.
Well, so I mean, I'm an observer, so that's how I kind of get my main body of evidence for everything. So how are you kind of researching this if you don't have observations of it happening?
Well, that's a very good question. First of all, observations are the difficult part, and I'll let you do that. The idea here is we take the physics that we believe to exist, and we use those from first principles and try to see what do they predict. We run big numerical simulations where we feed all our models into a big computer and let the computer crunch the numbers. And these direct collapse black holes, for example, are a prediction from these simulations.
Could you show me one of these simulations?
Absolutely. So this simulation follows how gas becomes denser and denser. And that's the way to forming the first stars, the first galaxies. What you can see here is, for example, you see along the filament, in the nodes of the filaments, which are very bright here shown, is where the first galaxies form. It's also the place where the cosmic filaments come together to form the direct collapse black holes, gravity starts pulling things closer and closer and starts forming these filaments, these sheet-like structures. And that's the cosmic web. It forms from the gravity pulling things together while the universe is expanding.
The cosmic web is the scaffolding formed by all the material in the universe. Vast tendrils of matter filled with hydrogen gas. Each filament can be millions of light years long.
What's special about the conditions at these intersections?
So we have a bunch of simulations that we run with our group, and one is that I'm showing you right now is regarding the formation of a black hole in the cosmic web. What you can see here is gas coming in along those filaments, which you see here in the form of the cross. What it does is it converts a lot of the energy that it gains during its infall into turbulence. And this turbulence stops the formation of a star once it reaches very high masses that you can see here by these red high-density peaks. It starts forming a black hole in there because it's just so massive that it cannot sustain its own gravity anymore. The children of the cosmic web, those direct collapse black holes that form, it's their birthplace.
Wow. Do we think that this is still happening at all?
The average density of the universe has dropped as the universe has expanded more and more. And that makes it also more difficult to have so-called high accretion flows that bring in lots of material, lots of gas from the cosmic web over a short amount of time.
So there was this kind of sweet spot of time in the universe when conditions were ideal to form these direct collapse black holes.
Absolutely. The cosmic nursery, as we call it, you form the first baby black holes, the baby galaxies. Basically, during the first billion years of the universe is where all that action happened. This is really the growth spurting period of the universe.
So is there any other way that direct collapse black holes could have formed?
Yes, there's, for example, the way of trying to get rid of the coolants, because the key in forming a direct collapse black hole is that the gas doesn't have the ability to cool down. And one of the very important coolants in the early universe is via molecular hydrogen. And molecular hydrogen can be dissociated by radiation, by UV radiation.
Molecular hydrogen, or H2, is one of the simplest and oldest molecules in the universe. In the early cosmos, it helped gas clouds cool and collapse to form stars. But if radiation from those first stars destroyed that H2, the clouds could keep growing until they reached a critical point.
Let me start the simulation. And there we go. So this is basically a simulation of this gas cloud in which you have no coolants. So red is very dense gas and blue is very underdense gas. And as the gas cloud collapses, it forms a disk in which you can form very dense clumps. So we have in the middle one clump that is making a direct collapse black hole, but also some of the other clumps are conducive of forming a direct collapse black hole. And the fascinating thing about that is these direct collapse black holes, they will start actually moving towards each other and merge.
But my question is, how confident are you that these direct collapse black holes can actually explain the little red dots we see?
So you might say, well, they have the right mass, the black holes that people suggest to be in little red dots. We have a mechanism to make black holes of that mass. So that's the first evidence we take. At the moment, it looks like a very promising path. But of course, I'm not going to rest until we have more and more evidence to say it is indeed the way to go forward.
What I really like about this story is that we've talked about all this complex physics, and then as an astronomer, I'm sitting here going, well, we've got a big thing, so either you must have had a little thing and then it grows really quickly, or you formed a big thing via some other process that produces big things. But that's where we've got to with this.
Yeah, but I agree that one of those two.
Those are our options.
Must be right. I sometimes get asked, isn't this terrible for you because you launched this telescope and you're seeing things that you can't understand. Why did we launch the telescope? Because we wanted to see structure formation in the universe. Because we didn't understand it.
People care about black holes. Why? What is it that excites the public about these things?
It speaks to our sort of fundamental attraction to the unknown, which is the foundation of science. The key to science is to stand on the edge of the known and gaze out into the unknown, not with fear, but with delight and excitement. And black holes are surely the best example of that. That's a photograph as far as we understand it, of the end of time in space. That's what it is, right, according to Einstein. So that's remarkable. You know, so the universe is far stranger than we could possibly imagine. The best argument I know for curiosity-driven research is black holes.
While black holes continue to challenge us, there's still plenty to feast our eyes on in late summer as we gaze up at the night sky. Guest presenter Dr. Becky Smethurst is here to tell us about it.
August can only mean one thing when it comes to the night sky, and that is, in my opinion, the best meteor shower of the year, the Perseids. Now, the best thing about meteor showers is you don't need any equipment to watch the shooting stars. You just need time for your eyes to adjust to the dark. Now, it can get uncomfortable craning your neck constantly up to look at the night sky, so I always recommend lying down to watch a meteor shower, like, for example, on a sun lounger, or as I like to call them, star loungers. Plus, we have perfect conditions for watching the Perseids meteor shower this year because the skies will be really dark for the peak around the new moon. Now, the Perseids are caused by tiny lumps of rock left behind by the comet Swift-Tuttle on its 133-year orbit around the sun. Earth passes through this rubble every year, and we see those tiny lumps of rock burn up in the atmosphere as shooting stars. And to top it all off, you can watch the Perseids at a normal time. So you can start looking in the early evening, just after the sun is set, around about 9 o'clock. So there's no late nights or early get-ups required. The peak will be on the night of Wednesday the 12th of August, but will continue to be active until the 24th of August. It's hard to predict just how many you'll see, but at its peak in the darkest skies, there could be anywhere from 100 to 150 meteors per hour. And don't forget, there will be a partial eclipse of the sun on August 12th, the same day as the Perseids peak. We really are spoilt this month, but remember, never ever look directly at the sun. Now, while you're out watching the Perseids or walking back from the pub at some point this month, look out for Saturn rising. Saturn will appear in the east about 11 o'clock in the middle of August, and then by the start of September will rise at 9 o'clock. But if you're not sure what you're looking for, I've got 2 tricks for you to spot Saturn. So the first trick is to know that stars twinkle, but planets don't. That's because starlight is just a tiny pinprick, so if any of that light gets disturbed as it passes through the Earth's atmosphere due to turbulence, that's going to make the star twinkle. Whereas the reflected light from a planet covers a much larger area. The second trick is to use the moon as a handy signpost. So on the bank holiday weekend, on Sunday the 30th of August, the almost full moon will be just above Saturn. So enjoy the sights ahead, and if you do want to share any images that you take, send them to the Sky at Night Flickr page. There's details on how to do that on our website, www.bbc.co.uk/Sky at Night. And here's a few that you shared recently.
Black holes, the ultimate agents of chaos and the architects of the cosmos. If we look up, we can see the evidence of the work of black holes all around us, in the stars and galaxies that shine in the night sky. Little red dots have not broken cosmology, as some scientists originally thought. They have added to it immeasurably. And how cool is it that now we get to study them? Good night.